Hello, and welcome to AI for Mechanical Engineering. In the previous lecture, I've covered some important topics regarding linear transformations of vectors. In today's lecture, I'll be revisiting the example from the system of linear equations and lay the foundation for solving optimization problems. So if we revisit the example for the set of linear equations, we first had unknowns and a number of equations. And the goal was to find the value of these unknowns. So in this example, x1 and x2 are the unknowns or variables. And out of all the possible values that x1 and x2 can have, we want to find the value of x1 and x2, or the unknowns, that satisfy this relation. So in a sense, these terms can be seen as constraints that are posed on the variables. Based on this formulation, we were able to take the constants or the coefficients of each unknown and represent it in terms of a matrix. Depending on the shape of A, we can either have a well-determined linear system, underdetermined linear system, or an over-determined linear system. And I'll be explaining in detail what each of these terms imply and how we can solve for the solution in each case. Starting with the well-determined linear system case, this example is actually from our first lecture, so we already know how to solve for the solution. Now in this case, we have an equal number of unknowns and an equal number of unique equations. And by solving for the solution of this set of equations, we have a unique solution. One important thing that I'd like to mention is that although we already know that this equation corresponds to a line, I'd like you to view this line as a collection of all possible values that satisfy this equation. So each of these dots along this line are potential solutions or potential values that satisfy each equation. And to solve for the value of the solution, we simply look at the intersection between the two lines, which is essentially finding the point that satisfies both equations at the same time. And the reason why I said that we need to have unique equations is because if the equations aren't unique, we end up with parallel lines, which imply that there aren't any potential or plausible solutions. So again, the takeaway here is that for a well-determined case, we have a unique solution. And if we revisit the example from earlier lectures, in order to solve for the solution, we formulate the system of linear equations into matrix form and use the inverse to solve for the value of the solution. And because we have an equal number of equations and unknowns, this matrix has a square form. Now moving on to the underdetermined case. In this case, we have a greater number of unknowns than number of equations. So in this particular example, we have two unknowns and one equation, implying that if we look at all the possible values for the solution, we simply end up with a straight line, and any point along this line satisfies this equation, meaning that it can be a potential solution. So this, in turn, implies that there are many solutions, in fact, infinite number of solutions, meaning that we cannot come up with a single or unique solution in its natural form. And again, if we represent this in matrix form, this time you can see that the matrix has a wide or broad shape. So given a set of linear equations, whenever the shape of A is fat or wide, we have many solutions. And finally, for the overdetermined case, In this case, we have more equations than unknowns. So if we try visualizing this, we can see that there is no single point that intersects all three lines at the same time, which in other words implies that no solutions exist that satisfy all three of these equations. Unless we're very lucky and assume that the third line passes through this exact point, in a typical case, we don't have any solutions. So if we represent this in a matrix form, this time you can see that the form of the matrix is taller than it is wide, implying that whenever a matrix is tall or skinny, we do not have any plausible solutions. In conclusion, we've looked at three major types of linear systems, in which the first case was square or well-determined, underdetermined where we had a fat matrix, and finally overdetermined where we had a skinny or tall matrix. And again, in the well-determined case we had a unique solution, and for the underdetermined case we had many solutions, and finally for the overdetermined case we had no possible solutions. Now let's assume that we had to find a solution for each case somehow. Now the first case is already done because we have a unique solution, but for the second case, since we have many solutions, we simply choose a plausible solution based on some sort of a metric or objective. So for example, if this corresponds to all the possible values of the solutions, we choose a point that satisfies or best fits our objective. This example is mostly seen in other fields such as control systems, where we're given a set of possible control inputs to the system, and our goal is to select a single optimal solution that drives the system to its target performance. In terms of machine learning, the most common type of matrix that we see is a skinny or an overdetermined case, where we have a lot more equations than unknowns. From the perspective of machine learning, each of these rows can be seen as some sort of a demonstration or example of a phenomena that represents the relationship between x1 and x2. And the goal becomes to find the values of x1 and x2 that best fit those demonstrations or data. So again, if we try graphically representing this, solving for the solution in an overdetermined case would be to find a point that seems to satisfy all three of these equations the best, which would be somewhere around here. Now I'll be talking about how exactly we can solve for the solution in each of these cases. And starting with the underdetermined case, let's say we have this set of linear equations. And we already know that this corresponds to a single line. Now in the previous slide, I've mentioned that we can select a single value based on some sort of a metric. And although there are different ways to select a single value, one type that is commonly used is to minimize the norm of x. So let's look at the control system example again. In terms of a control system, let's assume that this line corresponds to all possible actions or inputs to the system. And among these inputs, we're trying to find a value that minimizes the norm of x. This can be seen as minimizing the control efforts or energy among the possible solutions that satisfy this equation. So if we formulate this in terms of an optimization problem, our goal is to minimize the norm of x, which is our objective. And typically in an optimization problem, we write out the constraints as the following. Now if we visualize this optimization problem, because the goal was to minimize the norm of x, we see that the minimum value corresponds to this point, which corresponds to the point along the line that has the shortest distance to the origin. And if we write out the solution, we end up with something in this form. And since we've minimized the norm, we have our least norm solution. Again, I'd like to emphasize that this is more commonly seen in other fields such as control systems and is not typically seen in machine learning. So in this course, you don't have to memorize the form of the solution for the least norm solution. Now for overdetermined systems, which is typically the case we encounter in machine learning, this case we have a skinny or tall matrix. And just like I've described, we cannot find the values of x1 and x2 or the solution that satisfies all of these equations at the same time. So instead of trying to find a value that satisfies all of these equations, we try to minimize the error or the difference between ax and b. And so if we formulate this in terms of an optimization problem, the goal becomes to minimize the norm of the error, in which the error is defined as the difference between these two terms. Now, based on one of the ways that we can use to represent matrices, if you recall from earlier lectures, you can represent a matrix in terms of its columns, and by doing so, AX becomes a linear combination of the column vectors. And by doing so, we can visualize this set of linear equations in terms of its column vectors. So because AX is a linear combination of each column vector, AX simply corresponds to a hyperplane that these two vectors can span. Now if B exists along this plane, then we can find the values of x1 and x2 that satisfy all three conditions. In other words, there is an intersection between all three equations at the same time. However, this isn't typical, and in most cases we end up with something like this, implying that B is not within this plane. So no matter what value of x1 and x2 we choose, we can never construct this vector here. And the closest we can get to this vector is the projected value of that vector onto the plane. Now if we take a quick peek at what the actual solution is, we have this form. In other words, we've found the value of x such that creates our projected vector b star. Again, this least square solution is commonly seen in machine learning or estimation problems, as I've previously described. Now let's take a look at how we can solve for the value of x in order to find the value of b star. And before we look at the projection of a vector onto a plane, let's consider a simple case where we're looking at a vector projection onto another vector. So here we're projecting our vector x onto the vector y, which gives us our projected vector, capital W. And capital W can be defined as the magnitude multiplied with the unit direction of y. And for simplicity, we'll be denoting the norm of capital W as omega. So if we write out our projected vector, we have this form. Now from trigonometry, we can compute the length of this vector by multiplying the norm of x with cosine theta. So here's our first term. And from our previous lecture, we already know that cosine theta corresponds to the inner product over the norm of each vectors. Hence, if we substitute this into this equation and simplify, we have this as our value for omega. And finally, because our projected vector is defined as omega times the unit direction of y, the expression for our projected vector becomes the following. We can also further simplify this to represent the projected vector in terms of x, where p is equal to y transposed over transposed y. So this is the first way to find the projection of a given vector onto another vector. Now the second way to find our projected vector w is to use one of the properties that we've learned earlier on. So if you recall from inner products, if two vectors are orthogonal, then the inner product between those two vectors are equal to 0. So using this property, we can define this vector as x minus w and compute the inner product between this vector and this vector. So if we write this out, because we're taking the inner product between y and x minus w, and we're trying to show that this is equal to 0, we first compute the inner product between the two vectors and set it equal to 0. And by simplifying the equation with respect to omega or w, we end up with this final expression, which corresponds to the same results that we've obtained in the previous slide. So to summarize, the idea was to use the inner product of two orthogonal vectors to find the value of the projected vector. So we'll be using this second approach in the 3D example. Now this time, because we're dealing with a three-dimensional case, we have to show that this vector, in which we've previously defined as E, is perpendicular to this plane, or the span of A1 and A2. So the idea is to show that A1 transposed E is equal to 0, or the inner product between A1 and E is equal to 0, and at the same time, A2 transposed E is equal to 0. Again, the inner product between A2 and E. Now, satisfying these two conditions at the same time is equivalent to looking at the stacked vectors in terms of a matrix. So in other words, A transposed is equal to, implying that if we take the inner product between A transpose and E and show that this is equal to 0, we're effectively showing that each of these conditions are both 0. So if we write this out, we have the following equation, and simplify it in terms of x, we end up with our final form, which is identical to the least squares solution that I've shown in the previous slides. So again, this is a very important property and example, especially in terms of machine learning. So unlike the least norm solution, I'd like you to memorize the solution, or the least squares solution. In today's lecture, I've introduced some methods to solve for the solution of under and overdetermined systems, and laid the foundation for solving optimization problems. This concludes the lecture on linear algebra, and thank you.